Hello everyone, I'm Norman Wahlberger and welcome to Algebraic Calculus. In this video we're going to introduce polygonal splines, which are more general tools that will allow us to integrate over a wider range of paths. And in order to introduce these polygonal splines, we have to have a little bit of a look at data structures in mathematics. We want to talk a little bit about lists, ordered sets, multisets, and sets, and extend that discussion a little bit. Okay, so data structures are ways of organizing things in mathematics, objects typically, to create more elaborate or more complicated structures. And they're really very fundamental tools that we use to build up mathematics from simpler things. And there are four types of data structures that are commonly found in many different parts of mathematics, and this is of independent interest, and I talk about this quite a lot in my Math Foundations series, so if you want more information, there's quite a lot more there. So the main distinction is that there's really two kinds of questions that we can ask when we're talking about a data structure. We can ask whether it's ordered or whether it's unordered. And we can ask whether repetitions are allowed or whether they're not allowed. That gives us altogether four possibilities, and these are the four possibilities that are so important for us to understand. So the first one on the list is the list, which is a data structure that's ordered. In other words, the elements are occurring in a particular order. There's a first one, there's a second one, there's a third one, and so on. And repetitions are allowed. We are allowed to have more than one occurrence of an element in a list. So here's an example of a list. And it's characterized by the brackets that we use and the fact that we're using commas. So these square brackets alert us to the fact that repetitions are allowed. And the commas alert us to the fact that things are ordered. We have a first one, and then a second one, and then a third one, and then a fourth one. Now if we go to repetitions not allowed, then we get what's called an ordered set. An ordered set or an oset. And here's an example of an ordered set. So the difference is that there are now braces instead of square brackets. That means that every element that appears here may only appear once. So it's like a set, but it's ordered. There's a first one, there's a second one, there's a third one. Now, very important note of distinction. We should probably make a little mark here. Let's do that. Okay, so this is a non-standard kind of notation that we're introducing here. Actually, we talk a lot about it in the Math Foundation series. But we're using the braces and the commas to denote an ordered set, not just a set. Okay, so when we go to a set, we're going to have spaces instead of commas. The commas means that things are ordered. The spaces means that things are unordered. So maybe we'll move over here to the multiset. The multiset has repetitions and it's unordered. The repetitions are specified, or you can see that by the square brackets, and it's unordered because there are only spaces separating the elements. So you can think of these elements as freely floating around. And a set is just like a multiset, except that the elements can only appear at most once. Repetitions are not allowed. Okay, so these four different types of structures, very important, and it's very useful for us to have this very concrete notation, right, that tells us which of these four situations we're in just by looking at the object. We look at this, we see the square brackets and commas, that's a list. We look at this, it's got the braces and without commas, that's a set. So on, okay. So that's a very useful kind of thing. And we are going to be adopting this notational convention, these definitions, this terminology in this course. So please make sure that you get on board here. So our four data structures are captured by this little acronym, LOMS, LOMS, lists, ordered sets or osets, multisets or MSets, and sets. And they're discussed at quite some length in the Math Foundations C series, Math Foundations 150, and so on. So far in this course, though, we've actually used another type of organizational structure, that of a cyclically ordered set. So I remind you that when we introduce the idea of an oriented triangle, like ABC, with this tilde convention, that we said that this was essentially an ordered set, like A, B, C, with 3 elements, each of those elements being an affine point. But with the added condition or the added agreement that if we rotate the elements, if we take the A and move it to the end, you get BCA, or we do it again, take the B and move it to the end and get CAB, then all of these are going to be equal. So there's an order involved, but there's also an equivalence between these 3 different kinds of orders. All of them are captured by this notation here of the oriented triangle. Now this is a little bit confusing perhaps from a computer scientist point of view, because we're introducing this convention of saying that this ordered set is really the same as that ordered set. But as ordered sets, if you actually just look at these things, they're obviously not the same as ordered sets. So we're a little bit at odds with our data structure conventions when we try to introduce something like this. So we're going to be a little bit more sophisticated now, and we're going to tackle this problem by introducing another kind of data structure, a cyclically ordered kind of data structure. All right, so we're going to look at the 4 data structures that we have, and we're going to impose something else that captures the idea that's necessary for us to talk smoothly about oriented triangles, and then later on certain kinds of polygonal splines later in the lecture. So let's introduce a cyclic list first of all, and then a cyclic oset, or we might call it a C list or a C oset. What we're going to do is we're going to take the idea of a list, there's a list right there, and we're going to put pointed brackets around it. That's going to create a new kind of data structure, which we'll call a cyclic list. And what is it? Well, it's just like a list, but it has this cyclic convention that's exactly the same as one we've just talked about. We're going to agree that this cyclic list is the same as this one. What you get when you take the first element and move it around to the back and shuffle everything over. And again, of course, we can do it again. We get 4, 2, 1, 1. And then we can do it again. We get 2, 1, 1, 4. And if we do it again, we get 1, 1, 4, 2. We're back to where we started. So this bracket that we're imposing in addition to the square brackets tells us or alerts us that we now have a different kind of data structure. It's very close to being a list, but it's a cyclic list. Okay, it doesn't really have a start and an end like an ordinary list does. It kind of goes around in a circle. Okay, similarly, we're going to talk about a cyclic oset. It's also going to be another ordered structure. So these are the 2 ordered structures, list and osets. So a cyclic oset is an oset with an additional pointed bracket around it. That's going to tell us that we are imposing cyclic equivalence. So the oset 1, 2, 3, when we put the brackets around it like this, it's the same as the oset 2, 3, 1, the same as the oset 3, 1, 2. And instead of calling them osets, we'll call them cyclic oset. That's a cyclic oset. So this is, it's kind of nice so that we can now identify very easily on the page, that's a new kind of object. That's not a list, it's not a multiset, it's not a set, it's not an oset. It's a cyclic list, or it's a cyclic oset, and we know exactly what that means. So now we can, if we want to, return to our oriented triangles and sort of redefine an oriented triangle in terms of our new notation. An oriented triangle, ABC, is just the cyclic oset consisting of 3 affine points. And it's an oset. There cannot be any repetitions here, right? We're not allowing 2 of these things to be the same. They have to really be 3 distinct points. And more generally, an oriented n-gon, A1, A2, up to AN with another tilde on it, can now be rethought or redefined to be the cyclic oset A1, A2, up to AN. So it's the oset with the extra brackets. That means it's a cyclic oset, or C oset. And again, this condition requires that each of the AIs appears only once. Because it's an oset, repetitions are not allowed. So that ensures that every point AI occurs only once. But there's no requirement of convexity or anything like that. These points can go anywhere they like to be. So here's an example, A1, A2, A3, A4, A5, and then back to A1. That would be an example of a picture of the n-gon, the oriented n-gon, A1, A2, A3, A4, A5 tilde, which is the cyclic oset A1, A2, A3, A4, A5. So that's nice terminology that allows us to maybe think a little bit more broadly or more accurately about what oriented triangles and oriented n-gons are. But oriented triangles and oriented n-gons are great. They are very natural for geometrical investigations. But in calculus, we want to broaden the scope. We want to consider more general things. We want to, in fact, drop the requirement that the points cannot be repeated. When we do that, we get more general objects that are in some sense more easy for us to work with because we don't always have to be checking whether there's repetition or not. Okay? And these are polygonal splines. All right, so let us introduce oriented polygonal splines. These are more general objects than oriented n-gons. They're like oriented n-gons, except that we're being more general in two different ways. First of all, repetitions are allowed. We are now going to allow repetitions. And furthermore, closure is not necessary. We are not going to insist that the n-gon come back to where it started. So these oriented polygonal splines are going to start at some point, and then go to there, and then go there, and then go there, and then go there, maybe back to where we already were, and then go over here, and over here, and over here, and over here, and end there. They don't have to end where they started. And repetitions are allowed. So here is the official definition. And we'll introduce this little acronym, OPS, for an oriented polygonal spline. What is it? Here's what it looks like. A1, A2 up to AN with a vector kind of arrow, but notice it's different from the vector arrow that I usually draw. It's an arrow with a kind of two-sided barb, not like a harpoon. Usually I draw vectors like this. So this thing is a list of affine points. That's the definition. So A1, A2 up to AN with this arrow, that means this list of affine points. A1, then A2, all the way up to AN. This is a list. You can tell that because it's in square brackets and because there's commas. So repetitions are allowed and it's ordered. There's a first one, there's a second one, there's a last one. The AIs are, of course, affine points. That is then really a generalization of an n-gon, a very flexible kind of thing for us, very useful. And while we're at it, we're going to introduce a particular kind, sort of the simplest kind of such thing, which isn't trivial, is an oriented edge, when we only have two affine points, A1 and A2. And so we have an oriented edge, A1, A2, which is just the list A1, comma A2, end of list. And we'll call that an oriented edge. So that's a OPS, or oriented polygonal spline, of the form A1, A2. Okay, so now let me introduce an example, and we'll also talk about some additional terminology associated to one of these oriented polygonal splines. So here's an example. Let's call it gamma. It's the OPS ACBBECD with an arrow over it. And here's the picture. There's A, there's C, there's B again, of course, there's E, there's C, and there's D. Now, technically what this thing is, right, it's technically not a picture. Technically, it's just a list. So on your computer's hard drive, you know, if you ask the computer, what is this? It'll say, it's this. This is what it is. It's a list with the elements A, C, B, E, C, D in that order, and the list is enclosed in square brackets. That's what it is. But we can picture it usefully on the plane as a kind of path consisting of these linear pieces. That's why we call it a polygonal spline. So we're starting at A, and then we go to C, so we represent that with this line segment. And notice that I'm putting a little arrow halfway, roughly, between them. And notice that this is not a closed arrow, but it's kind of an arrow that looks like this one. Okay, so there's AC, and then CB, and then BB. Well, how are we going to visualize that? Well, we could, if we wanted to, make a little loop here just to alert us to the fact that there's actually something going on there. Right? We're going to B, and then we're repeating B. So the polygon is not really going anywhere, it's staying at B, but we're recording that fact here visually with this little loop. After we're at B, then we go to E, and then we go to C, and then we go to D. So notice that we're going back to C. That's all right, because repetitions are allowed in a list. So this polygonal path is allowed some freedom that a polygon is not. Okay, a polygon cannot do this kind of thing. Polygon cannot stay at a point repeatedly. It's not supposed to go back to where it already was unless it's the end of the loop. And also this thing is not closed. Okay, some extra terminology associated with this OPS are its oriented edges. So this thing has oriented edges, and we'll define the oriented edges of this thing to be the OPS AC, as well as CB, and as well as BB, as well as BE, as well as EC, as well as CD. So we just go through them, and we can list all of the oriented edges. Notice that BB is a legitimate oriented edge of this OPS, this oriented polygonal spline. We'll also talk about the beginning point. So let's say B of gamma is the first point. And the end point, E of gamma, is the end point, the final point. So B of gamma and E of gamma, maybe we'll try to remember those are the beginning and the end of our splines. And we'll say that the spline is closed precisely when these two happen to be equal. So if it's the case that we get back to where we started at the end, then we'll say it's a closed spline. In other words, the begin of the spline is the same as the end of the spline. So this is a flexible kind of notation. It's perfectly captured by our list data structure. It's very useful for calculus. Very, very useful. In some ways more useful than the idea of an n-gon. So we're going to leave the geometry behind a little bit and become a little bit more combinatorial or almost computer science oriented. Okay. So very flexible and useful notion. An oriented polygonal spline. And now, the signed area of an OPS. An oriented polygonal spline has a signed area, and we're going to define it now. And we're going to do that by defining it first for the simplest kinds of OPSs, the oriented edges, the things with only two elements. So if A is our usual point AB and B is our usual point CD, then the signed area of the oriented edge AB with that spline kind of arrow on top of it is, no surprise, S of AB is AD minus BC over 2. So if this is the origin and here's A and here's B and there's the oriented edge from here to here, then the signed area is just AD minus BC. That's just the signed area of that triangle OAB. It's almost the same as the signed area of an oriented side. What's the difference between an oriented edge and an oriented side? Only this, that the oriented edge is a list, while the oriented side is an oset. Sides have to have distinct points. Edges don't. We can have an edge of the form B to B. So that's our definition of the signed area of an oriented edge. And now we define the signed area of a general OPS, oriented polygonal spline. So if gamma equals A1, A2 up to AN is an OPS, there's a spline kind of arrow, then its signed area is, by definition, maybe we should put a definition sign here. Let's do that. So S of gamma is, well, it's the signed area of A1, A2, plus the signed area of A2, A3, and so on, all the way up to the signed area of the last pair, AN minus 1, AN. Okay. Okay, so we're just going through all the oriented edges in order and adding up all the signed areas of the oriented edges to give us the total signed area of the OPS gamma. Okay, but you remember at the beginning of the lecture, we started off by expanding our 4 basic types of data structures to also include cyclic lists and cyclic osets. So we want to do that here as well. We want to consider cyclic versions of splines. Cyclic versions of splines. Okay, that's what we're doing now. We're talking about cyclic-oriented polygonal splines. Bit of a mouthful. So the definition, a cyclic-oriented polygonal spline, namely COPS or COPS, looks like this. A1, A2 up to AN. But now look, the arrow on top here is a double arrow. It's like a spline arrow, but going in both directions. Okay, that's what the terminology is going to be. And what is it? Well, it's a cyclic list of affine points. Namely, what it actually is this. It's this cyclic list, A1, A2 up to AN. And it's a cyclic list because it's a list enclosed in the pointed brackets, which tell us that it's a cyclic list. So for example, have a look at this thing. There's an A, there's a C, there's a B, there's a D. There's also this little loop here. And now have a look at this thing here. This is D. It's the COPS, the cyclic-oriented polygonal spline, A, C, C, B, D. And it's cyclic because of that double arrow. You can see it. The double arrow's there. It's a cyclic object. This is a COPS. So what does it mean? Well, it means that it's something that goes like this. It starts here, A, and then goes to C, and then stays at C, and then goes to B, and then goes to D, and then goes to A. It's cyclic. It goes around in like a circle. There's not really a beginning and an end to this thing anymore. If it was a list, there'd be a beginning and an end. There's no beginning point, there's no end point, because this is a cyclic object. It also has oriented edges, namely, well, we just go through them. AC, CC, CB, BD, and crucially, one more than we get for just an OPS, also DA. So DA is an other oriented edge for this cyclic oriented polygonal spline. So notice that even though the arrows are going in both directions, we still read from left to right. We still start reading here and then we read like this. It's just that when we get to the end, we have to come back to the beginning again. And what this actually is, technically, this is only a picture, a representation of it. What it actually is on our computer is just this cyclic list, the list A, C, C, B, D, enclosed in the pointed brackets, making it a cyclic list. So it's the cyclic list A, C, C, B, D. So this is a kind of a repetition version of an n-gon. With an n-gon, you go around and you come back to where you started. So here we're also coming back to where we started. But the difference between an n-gon, an oriented n-gon, and one of these cyclic-oriented polygonal splines is that repetitions are allowed here. We're allowed to go back to where we were. We're allowed to stay where we are repeatedly if we want to. There's no restriction on the actual nature of the affine points in the oriented spline, in the cyclic oriented spline. So just as we define the signed area of an OPS, now we should define the signed area of a COPS or a COPS. So if delta equals A1, A2 up to AN is a COPS, a cyclic oriented polygonal spline, then its signed area is defined as follows. Its signed area is equal to, and again I probably want to make that a definition. It's a definition. Okay, what is it? It's S of A1, A2, so there's the first oriented edge, plus S of A2, A3, the next oriented edge, and so on, all the way up to the last one here, which is S of AN minus 1 AN, plus, crucially, plus one more, plus the oriented edge AN to A1, its signed area as well. So if this was just an ordinary oriented polygonal spline without that arrow there, then we would have stopped the definition at this point. But because of that arrow there, we're obliged to go back to the beginning and include that last oriented edge from AN to A1, which is also in this story. So for example, here's a simple kind of quadrilateral, A1, A2, A3, A4. And so the signed area of this thing as a cyclic oriented polygonal spline, A1, A2, A3, A4 with the spline double arrow, is the signed area of A1, A2, plus the signed area of A2, A3, plus the signed area of A3, A4, plus the signed area of A4, A1. And each one of those, of course, has the interpretation that we're now familiar with as that of a signed area emanating from the origin. So we've been rather fussy about definitions today, a lot of definitions, just subtle differences perhaps, but this is part of being a pure mathematician. This is a pure mathematics course, and if you're just entering university and starting off, on your career in mathematics, it's great to be exposed to this kind of fussiness, okay? And I hope you enjoy it. I hope you enjoy the precision of knowing exactly what we're talking about. Now, in the worked examples and the homework questions that accompany all the videos, you'll get more practice at seeing the distinctions play out in specific examples. So I urge you to go through those carefully so to solidify your understanding of these differences. Because terminology, maybe it seems as if it's relatively simple and easy to absorb, but it's easy to forget, and it's easy to not remember the notation that we used. So notation is especially important. We really like having good notation. And that's what we're aiming for in this course, choosing our notation very carefully. So there's much to learn, and I'm Norman Wahlberger. Thanks for listening.